In combustion analysis, we'll make use of switching from mass basis to mole basis. In combustion, we most often get the analysis of the products of combustion on a mole basis. So we'll look at combustion, and we'll look at products of combustion. So if I look at that, and let's say I'm given the following. So I'm given the following, and so we have CO2, CO, H2O, O2, and N2. So, and the YI is 10.2%, 0.4%, 14.3%, 1.9%, 73.2%. And so what we want to determine is XI. So we're interested in determining XI. And so the first thing we have to do is, this is the mixture. So this is the mixture of the products of combustion. So that's the stuff that's coming out of your exhaust pipe, out of a smokestack, wherever it is, wherever there was combustion. This is slightly incomplete combustion, there's water formed, etc. And so if I looked at the equation that we had, so I had Xi was equal to Yi Mi over the mixture molecular weight, I know what the Mi is for these. I can look them up in table A1. So I can look these up in table A1. The molecular weight of the mixture I have to find using the equation is the sum of the Yi Mi. And so if I do that, it's 0.102 times 3401 plus 0.004 times 28.01 plus 0.143 times 18.016 plus 0.019 times 32 plus 0.732 times 28.016. So if I do that, I'll get the molecular weight of the mixture is going to be equal to 28.29 kilograms per kilogram mole. So I can find the molecular weight of the mixture. I know the Yi, I know the Mi, and I'll do one example for finding the Xi, and then the rest you can find, and I'll fill out the table. And so the Xi of the CO2 is equal to 0.102 times the molecular weight of CO2, 4401, divided by the molecular weight of the mixture, 28.29. So we have that Xi is 0.159. And you can do the rest of the gases, and if I fill out this table, which I can do now, let me erase this so it looks a little neater. We have this is 15.9%, 0.4%, 9.1%, 2.1%, 72.5%. So there is a difference. There is a particular difference here, and it really depends on how far the molecular weight of the CO2 is from, of the gas is from the molecular weight that you have. And for homework related to this, do 11.1 and 11.5. And now what we're going to do is let's look at our first law problem using this example, or using an example. So, all right. And this is just like what I did with the tank, where we had the air and we added heat. Now we're going to do the same type of first law analysis that you know how to do, except we have to find the mixture properties. So the same process we go through, system, substance, process, etc., we keep doing, except now the substance is where we have to determine the properties for the mixture. So we're going to have a mixture of 0.4 kilograms of helium. We're going to have 0.2 kilograms of oxygen. And we're going to compress it. So we're going to compress it, and from 100 kPa and 20 degrees C, and P2 will be 500 kPa, and this is PV to the N, and so it's a polytropic compression where N is equal to 1.4. And we want to find Q and W. So I want to be able to find the heat and the work. So what we've done is we did the sketch. It's a closed system. Substance is a mixture, ideal gas mixture. The process, PV to the N. So for a polytropic process, we know that delta U, so I know that Q is equal to delta U plus W. W is equal to M R sub M times T2 minus T1 over 1 minus N, and delta U is equal to M C sub B of the mix times T2 minus T1. So if I solve for these two, I solve for Q, and I know what the result is. So we have that. And so now what we're going to do is we're going to find out, we know the total mass, so M is equal to 0.2 plus 0.4 is 0.6. I know that XO2 is equal to 0.2 over 0.6 is 0.333. And XN2 then is 0.667. So I have what the XI are. And now I can find the C sub V and the R. So I need C sub V and R. So C sub V of the mixture is 0.667 times R times C sub V of helium 3.1189 plus 0.333 times, I'm running out of blackboard, so times 0.6585. And so I have that C sub V of the mixture is equal to 2.3, and R of the mixture is 0.667 times 2.077 plus 0.33, I'm doing it again, times R of the oxygen, 0.5298. So we're going to have that R sub M is equal to 1.47. So I have what these values are. So I have what these values are, and now I need T2. So we know that for a polytropic process, where PV to the n is equal to a constant, T2 over T1 is P2 over P1 to the n minus 1 over n. We know all this, we know all the values except for T2. So T2 is equal to 293 times 500 over 100 to the 0.4 over 1.4. So we have that T2 is equal to 464 degrees K. And if I substitute in, I have delta U is equal to 235.98 kilojoules. W is equal to minus 377.05 kilojoules. And Q is equal to minus 141.07 kilojoules. And so what we have with the piston cylinder, so if I look at the piston cylinder, I was putting work into it. So the work I was putting in was 377 kilojoules. Where did it go? Some of it went to increasing the internal energy to 236 kilojoules. The rest was lost as heat, and the heat had a minus sign, so the heat went out. So the energy is balanced. This is where it went. So a homework problem related to problems like this would be 1121. So we want to look at 1121 and see what that's for.